Okay, so today I'm going to talk about convolutional neural networks. That's our topic. We'll talk about networks, what's a network, and we'll talk about network representations, then we'll talk about convolutions itself, neural network, and then some applications that will I think that will take me like more than 2 hours, and I think we will have today some talks. Let's go to the okay. Where are my one more up? Class materials, yeah, okay, good. So paper presentation and reservation. Today is December 21st. And today we will have just a single talk by Başak. Başak, are you here? Başak? She is not here. So that means what? Do we have any other talks? No. So next week we are going to have 2 talks. Miraj, are you here? Miraj? Is Miraj here? No. Niyazi is going to do it next week. You want to do it this week or next week?
Next week.
Okay, so Miraj and Niyazi is going to do it next week, and after that we will not accept any presentations. So if you don't do the presentations, you know what's going to happen. Okay, good. Let me start talking about today's lecture then. Am I? So are you guys hearing me, online people? My online audience, do you hear me?
Yes, sir.
You do. Okay, thank you. Good. Okay, so let me start talking about this stuff. Okay, networks. I mean, the network itself. Networks are very popularly used and important part of computer science, computer engineering, and almost all the areas of science. And we are going to talk about structures specific for network. Whatever area you are working on, doesn't matter. One way or the other, you are going to work on the networks. You are familiar with the networks, okay? Okay, without the networks, entities in the real world are represented as dots, okay? This is a person, another person, another person, another person, etc. With a person, you would have a feature vector, maybe the age of the person. That person is 33 years old, a male, and a height of 175, and a university degree. The address is here, and etc. So these are the properties of a person. But we like to show the relationship between the persons, okay? For example, this relationship could be like, this is a parent relationship, okay? P2 is parent of P1. Or another relationship would be this P3, okay? A friendship relationship. So we show the relationship between these points on these kind of spaces using networks, and they are very useful, and this is just an example. Another example would be, these are the persons. Another example would be like this, okay? Would be like this. This is a city 1 and this is city 2. These are the neighboring cities, okay? So the relationship shows between them is the path between these 2 cities. So they are neighbors to each other. Or another one could be, for example, a drug, a disease, and drug, okay? This drug is used for this kind of a disease, and drug number 1, disease number 1, drug number 2, and disease number 2. This drug is used both of them. Okay, so these kind of networks are possible too. So the possibilities are actually endless, and we use these kind of representation techniques for all the areas of engineering and science. So why don't we have specialized networks, neural networks, or machine learning approaches for these kind of structures? That's what we are going to look at. It is getting more and more popular, these kind of neural networks. Okay, machine learning, specialized machine learning systems. That's why we like to look at it. So far, the data that we looked at are usually a grid-like data, like this, right? Grid-like data. So for this grid-like data, we use convolutional neural networks, okay, because it was very suitable for this kind of stuff, okay? Or we have sequential data like that, okay? For that one, for these type of stuff, we use CNNs. For this kind of stuff, we use RNNs, okay? And some combinations of those. But this kind of stuff, you could use an RNN for this. You could use a CNN for that, or you could use just a pointwise neural network application like a standard data. We could do that too. But we like to develop specialized techniques for this kind of data because they are so important. Okay, so this is the network. Some of the popular network examples, social networks. Okay, this person knows that person knows the other person, and that. For example, your LinkedIn network is a social network. Okay, LinkedIn network is a social network. What is the theory? Theory says no, it's not a theory. The observation is this. If this person knows this person, and this person knows this person, and this person knows that person, I think the farthest distance between any two persons on this world is maybe 4 or 5. I don't remember. Okay, take any two persons in this world, any two persons, you can follow the length of their friends or the people that they know. At most, at 5 hops, you will reach the other person. Doesn't matter. For example, I know Muhtar. You know what is the English name for Muhtar? My city part mayor. I don't know my Muhtar. I know my Muhtar. My Muhtar knows. My Muhtar knows the governor of this the city, right? And the governor knows the president of Turkey, and president of Turkey knows the president of USA. So it makes my Muhtar and the governor and the president, 4 hops to the president of USA, okay, or president of the Russia, or president of somewhere, okay. And after that, you can follow the downlinks down there, okay. So 4 or 5 hops. So people are disconnected. Why don't we use this information? I mean, if two people know each other, that's a very valuable information, and use that information to do, for example, how does the LinkedIn suggest you new friends? Say that you are connected with all those kind of people, and they are connected to all these kind of people, and it looks like your features are similar to each other. So do you know this person? Do you want to be connected with this person, and etc. Okay. Economic networks. Okay. What does that mean? For example, let me come back to this later. Before that, there are more important stuff. Maybe biological network, we are going to look at it. Internet is a network by itself. Okay, so let's look at this by internet. Let's look at www, World Wide Web. Right, so it is a sub part of internet. If each site is giving a link to the other sites, so they are kind of connected. So maybe this guy is Wikipedia's website. I don't know. It is anti-centered, everybody is referring to it, so it is referring to everybody. So this is a very important network. Information network, web and citations, yeah, this is important too. For example, this paper is citing many other papers, and many other papers are citing this paper. So that if you do the analysis, you would find some of the key publications that people have been citing, and some of the key publications that are the causes of some of the areas, and etc. Okay, so that's good. Okay, this is a network of neurons. Okay, maybe some of the neurons are related to visual data processing, and some of the neurons are related to hearing sound processing, but they are connected to, but I like to separate them into two groups: visual neurons and sound-based neurons. I like to separate them into two, so the network segmentation problem comes in. So networks are very useful. They are very commonly used, popular, and we are going to look at the network stuff today. Okay, universal language for describing complex data. Okay, and it doesn't matter if I am a computer scientist. When I look at the network of some other fields data, such as from biology or statistics or economics, doesn't matter, I understand what it means. So shared vocabulary, we know that. And the availability of data is very important, because this LinkedIn data is available, this health-related data is available, technology data is available, and etc. So the data is there. If we develop techniques, we can achieve very useful stuff like the social networking, social media, and drug design. We are going to look at this application later. Okay. So classical tasks, node classification. Okay. What does the node classification mean? Look at the, for example, for I don't wanna, because if I give it this example, I am going to, I mean some of these are overlapping. For node classification, for example, if you have the network of all the connected neurons on a cat's brain, okay, if you have such a network, I like to classify the neurons based on what kind of functions they are doing. Is this a visual processing neuron, or the audio processing neuron, or some other kind of neuron? So that's the node classification. Ring prediction. Okay, so node classification basically means that, okay, what is this node? Is this node an A-type node or B-type node? Okay, that's what it says. The other one is link prediction. Link prediction. Should there be a link between this one and this one? Okay, if there can be a link, maybe I can offer this. For example, this one is person 1, and this one is, for example, a camera that you can buy. Okay, camera A. If I think that this person would buy this camera A, and I am Amazon, I can offer this camera to this person, and I am thinking that there would be a link between. So this is a link prediction, or like the LinkedIn does. LinkedIn says that maybe you two guys can be connected. Okay, community detection. Detect a sub part of a network, or we can call sometimes graphs. Okay, and you say that this sub network of this network is related to each other, so I am going to call it a subgraph. For example, if these are the people on Twitter, okay, and if I link them using their retweet relationships between them, find me the people who oppose the vaccination, COVID vaccination. So if I can find something like that, when I say, okay, this is the sub network of the whole network that is opposed to vaccination, that would be a useful thing, okay? That would be a useful thing. Maybe I'm going to use that, maybe I am going to use that information to know what kind of information they are getting. Where are they getting their information about the vaccination or the COVID stuff? So these are all very useful stuff, and community detection, link prediction, node classification, or network similarity, how two networks are similar. I have two different networks, are they similar or not? So these are some of the machine learning stuff that we can use. Okay, node classification is this. I know the classes of these. What are the classes of these nodes? Okay, that's one thing. Okay, node classification. Link prediction, again, the example that I gave you. Okay, content recommendation is link prediction. Okay, if somebody is giving me this picture, okay, this is the content of it. Leather, laptop, bag, okay, and those are the contents. So this one belongs to both, okay, this one belongs to get, the both want to get context, also my stuff context. So given these relationships, should I offer a link for there? Okay. So basically this is, I mean, it doesn't matter what we do, we first try to represent our data using some kind of a feature vector, okay? We like to make it structured, okay? So we did the same thing for the words. Remember, we wanted to represent the words using the vectors, and we wanted those vectors to be similar to each other if the words are similar in terms of syntax or semantics. Doesn't matter. We try to do the same thing for the images. If two images are similar in their content, we said that maybe we should assign a similar vectors to those, and we are going to do the same thing here. For the nodes of the networks or the graphs, okay, we are going to assign similar vectors so that I can talk about them in a neural network or machine learning stuff. Okay. So that's what we are going to do if we are going to run this kind of a thing. Once I can represent the network nodes or the graph nodes, then I can talk about supervised or unsupervised machine learning for the networks or the graphs. Okay, so that's what we are going to do first, feature learning in graphs. How can I represent this node U as a vector in the D dimensions? Okay, like I did the same thing with the words. Okay, I wanted to represent a word as a D-dimensional vector so that the similar words have similar vectors. That's what I said. Okay, this is a very classical example. Zachary's karate club network. This guy has a karate club, and the nodes are the persons. Okay, and the arrows are the relationships between them. Okay, they know each other and etc. Okay, if I run this classification stuff. Okay, if I run this classification stuff, I know that I am going to classify the nodes for itself, but this is what I want to do. If I wanted to represent each of these with a two-dimensional vector, and if I put these two-dimensional vectors on this map, this is what I would get if I do it correctly. Okay, so it looks like the ones that are related to each other, the same colors are placed around here, there, and these purple ones are like this, but it looks like I am not doing very good between the purples and the green ones because they are kind of within each other. Okay, So this is a good representation method, but it is not as good as what I want. Okay, well, these kind of things will happen, but we would say that, I mean, this is a good result considering that I am only using 2 dimensions. Okay, well, it's a hard problem, I know that, because it doesn't fit to any of our models that we have seen so far. I mean, it is not grid-like structure, like the images or that kind of stuff. It is not like one-dimensional structure like the sound waves or the words. And it is like not like an instance vector without any relation to anything else. So their structures are a little bit different. That's why it is different from the rest of the stuff that we looked at. It is, I wouldn't say it is hard. I would say it is different from the rest. So it needs its own special ways of looking at stuff. Okay, so in this lecture we are going to look at this structure. So first we are going to look at the node embeddings. Okay, how I would embed the nodes. Then we are going to look at the graph neural networks. Then we are going to look at 2 of the applications which are kind of important. By the way, I have stolen these slides from off the web from these persons. Okay, I thank them. Since I am broadcasting this to all over the world, if they are listening to this, thank you guys. These are nice slides, and these are not mine. At least now I am giving credit to when I am taking these slides. Previously, I couldn't remember where I took them, but okay. I guess this is something not nice, but I'm not taking credit. Okay. Good. Okay. Let me start talking about the first part, the embeddings. Okay, node embeddings. Again, remember this one? I like to convert these nodes, each of them, to a d-dimensional vector. That's what I wanted to do, d-dimensional vector. And this embedding, I think I am going to close this window maybe and open somewhere. So, I am going to assign vectors to these nodes so that these vectors are similar for the similar nodes and different for the different nodes, and etc. So for this one, let's make a definition of a graph. So graph is a set of vertices and edges. Vertices are these. Okay, this is one vertex, another vertex, another vertex, and these are the edges. One edge, another edge, and another edge. Okay, so we have vertices and edges. This is a set, another set, and sometimes I represent it with an adjacency matrix. So adjacency matrix is something like that. Okay, let's say this is my graph. Okay, like this. This is node number 1, 2, 3, 4, and this is my adjacency matrix. Okay, 1, 2, 3, 4, 1, 2, 3, 4. 1 is connected to 2. Okay, there is a 1 here. 1 is not connected to anything else. Okay, and 2 is connected to 3. Yeah, and 2 is connected to 4, and 3 is connected to 2, nothing else, and 4 is connected to 2, right? Like that. Okay, so this is an adjacency matrix. Well, in this case it is symmetric. It is symmetric around this line, but it doesn't have to be, because sometimes these edges are directional. Okay, sometimes, for example, this parent-child relationship. One person is a parent of the other one, but the other one is not the parent. So it's not symmetric all the time. But in this case, it looks like it is symmetric. So let me remove these arrows. Okay, and this is called an adjacency matrix. Okay, so adjacency matrices are good ways of representing these neighbor or adjacency information or neighborhood information, because it's a matrix and we like matrices. Why? Because we can do multiplication and etc. with the matrices. Okay, good. So when we embed a node, exactly like the word embeddings, we want this. Okay, there is an encoder function that takes this node U, and it maps into the embedding space, 2-dimensional, 5-dimensional, 100-dimensional space. Okay, and I can transform each of those nodes to this embedding space. Okay, that's good. And while I am doing this, I should make sure that these two nodes, since they are neighbors, okay, in this here, these two nodes should have similar vectors. We measure the vector similarities by this cosine distance between them, right? We do the dot product between them. Okay, so come up with an encoding method, and design a similarity method accordingly. Okay, that works this way. Similar nodes should transfer to similar stuff, similar vectors. Okay, so that's going to be our design. By the way, when I say similar nodes, well, how do you measure the similarity of two nodes? That's going to be another problem. I don't know yet. Okay, so learning node embeddings, that's what we are going to define an encoder, define a node similarity function, and optimize the parameters of the encoder so that I can achieve this. Okay, so encoder, a similarity function, and similarity function is a measure of similarity in the original network, and I have to define that one too. Okay, encoder and the similarity function. Okay, again, I'm going to keep using this one. Remember, for the word vectors, we use this dot product between the vectors. If they are similar, this dot product should be large, because I mean the angle between them would be close to 0, those vectors, and the cosine of 0 is 1. Otherwise, it would be small, close to 0. Okay, so let's look at some of the embedding methods. One of them is shallow embedding, encoding or embedding. Okay, it is just an embedding lookup. Okay, instead of giving you this idea, let me show you this. Okay, you just give me one large matrix, and this one large matrix, every node has a column. For example, this column corresponds to a node. Okay, node like this one. 1, 2, 3, 4, 5, 6, 7 nodes, and this one is going to have 7 columns. Okay, each node has a column, and that column represents the represents the node itself. Of course, each column is a unique, okay? So all you need to do is just look up this matrix, very large matrix for the large networks, of course, and that's going to be your embedding vector. But I didn't tell you how to calculate those vectors yet, but this is just one way of keeping them. This is called shallow encoding. Okay, that's called shallow encoding, and it is based on each node is being assigned a unique embedding vector using one of the algorithms that we are going to look at. Okay, so how do we define the node similarity? There are many ways of defining the node similarity. How do you say that these two nodes are similar? Okay, we are going to look at them, but some of the things, are they connected? If two networks are connected, okay, we can say that they are similar. If two nodes share the same neighbor, we can say that they are maybe similar. And if two nodes share the structural rows, if their neighbors are kind of the same structurally, we can say they are similar too. So each one is going to give us a different way of measuring the similarity, and let's look at this idea of similarity starting from the simple one. The first one is adjacency-based similarity. Okay, with the adjacency-based similarity, this is what we would do. This is our adjacency matrix. Okay.
Hocam, can I ask a question?
Sure.
All we talked about the nodes, their features in the network, but we didn't talk about their attributes. For example, do we have some attributes for nodes or just their roles in the network?
Yeah. Well, I mean, these are shallow similarity stuff. If you like to use their attributes, for example, each person has its history, its age, and its gender, and etc. Those are kind of deep similarity measures, and we are going to talk about it right after this one. But that's a good point. We are only talking about the network structure here. We are not talking about, so each node is like a point without any feature, right? And we are talking about their neighborhoods and etc. We will come to that in a few minutes. Okay, that was a good point. So the most simplest similarity, maybe a yes-based similarity, it says that I am going to define my loss function this way. For all the node pairs in my network, in my graph, okay, I will dot product their vectors, okay, and I will subtract the adjacency value between them. Okay, so what does it say? It says that the dot product between the vectors of these nodes should be the same as their adjacency matrix value. That's what it says, right? So this one is trying to learn the adjacency matrix for the whole network. Okay, and that's my loss function. So this adjacency matrix, I mean, remember the adjacency matrix that I drew on you a few minutes ago? I said that it is like a binary network. It doesn't have to be binary. It can be, for example, city of A, B, C, D, E, F, and G. These are the cities. And these are the distances between cities: 200 kilometers, 250 kilometers, 75 kilometers, and etc. So now I am using the weights I am using the distances between the cities as the weights. So this adjacency matrix could be not binary, but the weights too. Okay. So if I optimize this loss function for the network, for the given network, I would end up, so what kind of parameters I am what kind of, okay, this should have been written like this, right? Loss of this parameter theta. Theta is our complete vector lookup table, okay, adjust the parameters of this theta in a way that these subtractions are producing zeros for the whole thing, and I am going to assign those numbers to those nodes, okay. So if I can do that, I mean, for the word to vec, I did something similar for this one, for the vec, I did something similar for this one. But if I can achieve this, that means that I can embed this neighborhood information into this vectors. And that's called adjacency-based similarity. Okay, this similarity is only measuring the adjacencies. It is ignoring all the features of the nodes. Yes?
ZUTZV, it's a scalar, but the other one is matrix. How we subtract scalar and matrix?
Well, this is scalar. This is the matrix element at this UV.
We use that element.
Yeah. Well, I mean, U is this. U is this. U is this. This is U and this is V, right? This UV is here. This is scalar.
Okay. We should do this considering the matrix is symmetric.
Well, it doesn't have to be symmetric because the distances between these sometimes, I mean, especially the distances between the two parts of the town, because sometimes the roads are one way. Sometimes you have to go all the way there and come back. And if you think about it, is easy to come to Istanbul from Ankara than going the other way because you are going down the hill. You're faster sometimes, most of the time, and the traffic is lighter for some reason during the daytime. So, I mean, you don't have to be symmetric all the time. Okay, you don't have to be symmetric all the time. Okay, good. So this is adjacency-based similarity, and this is how I optimize it. And usually, I mean, there are some methods to solve it without using any gradient descent numerical approach, like the matrix decomposition. It doesn't work all the time, so people usually do it with the stochastic gradient descent. I have numbers to optimize, the parameters theta, and optimize them. After some iterations, I will say this is sufficient, good enough for me, and these are your nodes now. Okay, so this is called adjacency-based similarity. And well, of course, this adjacency-based. But tell me what is wrong with the adjacency-based similarity. The one thing is your point. This one ignores completely the features of the nodes. That's one thing. What are the other things? What kind?
There's no depth. I don't take into account.
Yeah, it doesn't. It does not consider the other neighbors of it, right? Well, I mean, in effect, if U and V are similar, and if V and Z are similar too, their dot products should be close to 1 in a way that I can say that U and Z are similar, kind of, but directly I cannot say that U and Z are kind of in the same neighborhood. Okay, so that's kind of missing too. But I mean, that's how we define it. That's how we solve it. Maybe for many problems, this is good enough, and it will work. Okay, so that's called adjacency-based similarity. Of course, this is the runtime. O V square. V is the number of the nodes. I need to run this loss all the time. So this is expensive. Okay. Number of parameters is V times D. That's expensive too. Okay, and it only considers direct and local connections. Okay, so this one. Okay, the blue node is obviously more similar to green than compared to red. So these two are not neighbors. These two are not neighbors either. But I know that blue is more similar to green. I am not going to capture this information very reliably with this kind of an approach. So let's move on with multi-hop similarity. With the multi-hop similarity, we consider, okay, let's say this is our node. I am going to represent this node with a vector. One connection away things, okay, 2 connection away things, and 3 connection away things. So 1 hop, 2 hop, 3 hop neighbors, okay. So that's what I'm going to consider now. This is called multi-hop similarity. And with the multi-hop similarity, I just extend the idea of adjacency matrix approach, okay. K means the hop number. So if I am doing a 0 hop, okay, this is 1 hop. Previously, if I say K is 1, it reduces down to adjacency matrix approach, it reduces similarity. But if I increase K to 2, 3, 4, then I am changing my stuff, okay. So that's the idea. So change K, train multiple different hop lengths and concatenate output. So train this for K1, which is going to be the adjacency similarity, for K2 another vector, for K3 another vector, for K4 another vector, and concatenate all the vectors together, and you will end up with neighborhood sensitive similarity measure. That's called multi-hop similarity, okay. Another option for this multi-hop similarity is measure the overlap between node neighborhoods, okay. These two are not neighbors, but they have 2 connected stuff, okay. So LinkedIn probably is using this one much, because whenever it offers me a new person, it says that you and this guy know 50 people in common, okay. So you are part of the same same group. Maybe you should be connected to this person, okay. So something like that. But I mean, if you do this, it's kind of doing that, but you can do this in a separate way, like this one, okay. So this is multi-hop similarity other than the adjacency matrix, okay. So how many nodes do I have in common between the neighborhoods of these two, U and V, okay. Is the neighborhood overlap between U and V given someone, okay. So yeah.
Does it count only the direct neighbors, or for example, if we 2 hop, we have someone in common, does it count also in this function?
Well, of course, I mean, by changing the K value, you can enlarge the circle and enlarge the circle, okay. In this K is 1 here, okay.
For example, in this one, you use 2 nodes and they have 2 connections, completely direct connections in overlap. But let's consider the nodes at the ends. How are we gonna make these circles? How are we gonna?
Okay. These purple ones are the K3 neighborhoods, right?
Yes.
Inside this K3 neighborhood, I can count all these nodes and do the same calculation for given another node, K3 nodes, and overlap them. That's going to be
count all the nodes inside the circle.
Yeah, sure. And well, we count only the overlaps.
All
Yeah.
overlaps.
But if you keep this K2 big, what did I say before? If you take K like 4, 5, all the people in this world know the other people in this world. Okay, so it grows very, very fast exponentially. Okay, so we looked at those. Okay, so issues so far we have all of them. Expensive because I have to check all the neighborhoods. Okay, we are hand designing most of the stuff and massive parameter space. I am assigning 1 vector for each node. These are some of the stuff that we know. One other problem with this approach, can you tell me, I mean, other than these, the vectors that we are producing, there is a very serious problem with these kind of approaches. They only work for what?
2D networks. 2D networks.
No, these are not 2D networks. What do you mean? Well, they would work it for that too, because if somebody is not connected to anybody else, then this network will be
vector of zeros.
Yeah, well, for the adjacencies, yeah, it will be isolated. You cannot do anything much about it. But there is something else. These embedding systems work only for the nodes that it has seen before. If I have a new node, okay, if I have a new node that is added to my network now, okay, what kind of things should I add to it? Okay, what kind of representation should I add to it? That's going to be a little bit. I have to recalculate everything from the beginning, right? So that's not going to be good. So we are going to look at it in a few minutes. But it looks like I am out of time. Let's take 15 minutes of break. Okay, let's be here around 15:05. Okay, 15 minutes. Maybe I should go a little bit faster, but okay, it's okay. I will go faster. What happened to other people? Are they gone? Can you guys hear me? Where did you go? I had, I don't know what happened. Anyway, okay. I am not seeing this wrong, right? I have just only one. That's me. Okay. So let's look at some alternative ways of doing this embedding. Okay, that's called random walk. It's a very simple idea, but it works. Okay. I will start from this node U and start walking randomly over the neighboring nodes, and then take some nodes, and that will be my vector. Okay, that's the idea of random walk. Okay, when I start from U and visit my neighboring nodes in a random way, what is the probability that I can see this V? Okay, what is the probability? So I have to do this over and over and over again. So that's the idea. I started from U. Okay, I started from U. I can go this way, this way, this way, this way. I chose this way, then I chose this way, and I met this one. Or I started from U, I went this way, and this way I met U, V. Or went it this way, and that way. Or I walked the other ways, I didn't see it. So what is the probability that I can see V if I start walking from U? Okay, that will be my probability, and I should set my vectors Zi and Zj in a way that, okay, that would give me this probability. Okay, so I'm going to use this technique. Okay, so this idea is nice. Why? Because it is expressive. Okay, it's a flexible stochastic definition. It incorporates both local and higher order neighborhood information in a way. Okay, and it is probabilistic. If I do this more, at the average, I can expect that this is expressing all of my features regarding my neighborhoods. Okay, and it's efficient. Okay, I don't need to consider all the other nodes to calculate the node embedding of a given node, because I am only walking in my local neighborhood. I might have millions of nodes in my network, but I am only considering my neighborhood. Okay, which might be a few hundred nodes. Yes.
How many steps we should take in this random box? How many nodes we should go further?
Well, it's how many steps should I take? It's a parameter for the algorithm, might be K. Well, I don't know, but again, it shouldn't be too large.
How many of the adjacent nodes I should try?
What's that?
How many of the neighbor nodes I should try local? It has, for example, in this node has 5 nodes at its local neighbor.
Your question is same as how many layers of nodes should I have in my neural network? I mean, nobody knows the answer to that. Okay. You just test it.
It's a little bit complex to understand the random walk.
So I mean, you know the upper bound, right? If you take more than 5-6 steps for most of the networks, you are going to reach everybody. Okay. Again, but I mean, this one doesn't say that you shouldn't reach that one. The probability of you are reaching that other guy in 6 steps is going to be very, very small. Okay, so what's the difference between very, very small value and 0? Not much, so maybe you shouldn't take that much. So it's a trade-off between how precise you wanna be and how much time you have. Okay, so again, test it. I don't know the answer. You have a question? Yes.
Is there any constraints about the it can walk at the same nodes just once?
No. Well, you can run in a loop too.
But it can walk inside of the closed loop and it cannot go to anywhere.
Yeah. I mean, there is no. I mean, for this algorithm at least. I mean, the most general one, you could do this.
Yes.
That's possible. And that's why this one has a very high probability of seeing this one if you make a random walk, because it's a direct neighbor. Because you can, if you run in loops, then you are going to see this a few more times. Okay.
But it defines a new random route every time.
Yeah. Well, it's a random. I mean, this is one direction random, another random direction, another random direction, random, and random.
Random at each step.
Well, I mean, you have better chances of seeing this one twice than seeing this one once, right? So that's why this is more important to you. That's a nice thing. Okay? And we optimize the embedding to encode these random walk statistics, and it turns out that this works better than the other two. Well, not all the time, but most of the time. Okay? And this is the loss function now for all the elements in my network. For each U, I should consider the neighborhood of that U for some area, and inside that area, I should calculate this minus log likelihood of this probability. Okay, and optimize the embeddings according to this criteria. Okay, this is a multiset, by the way. This NRU is multiset. What's a multiset? It's a set, but you allow the same element to occur more than once. Okay, because I can visit the same node over and over again. It's a multiset. Okay, and we are using our regular softmax function to make this decision given this ZU, okay, starting point, the probability of seeing this V, and we use this our regular softmax function because in this case I am going to have many elements in it. So this is going to make it a little bit complicated. Why? Because to calculate, I mean, our loop is here nice. This is V. This is like maybe square root of V. This is a small number compared to that one. So we are lower than V square now, much better than V square. But calculation of this P is going to be expensive. But for this one, remember the denominator of this expression. Calculate this value for all possible V combinations, so that's going to be N square now, okay, or V square maybe I should say. It's going to be V square. That's not nice. We have to come up with a better way of doing this. So what we are going to do is we are going to calculate this value for some subset of all the V's, and we are going to call it some terminology, and we are going to see it in a few minutes. Okay, so nested sum over nodes or V2 complexity. I don't like that. Okay, so what we are going to remember, we had this problem in our word2vec application. In word2vec, we said that to compare this vector with all the other vectors of the vocabulary is going to be a problem. That's why they have invented this negative sampling. Do you remember that negative sampling? You don't run this loop for all the nodes in your network, but you run it for some random sample of it, okay, random subset of it, okay, and you assume that this is now representing the whole network. That's called the negative sampling, okay. So the top part is okay. These are the ones, okay, that I'm measuring the similarity, but the denominator, I don't have to I don't have to compare this for all the between all the possible node pairs. Instead, I am doing this with a random distribution over all nodes. So remember, with the word2vec, you specify a negative sampling value like 20 or 30 words, and you are going to do the same thing for here, 20, 30 words, instead of testing it 20 or 30 nodes, instead of doing it for all the nodes, which is maybe a few thousand. So that's called negative sampling, and we do this, okay, we do this for this random walks calculation of this softmax. Okay. By the way, when we say we randomly walk, what is the meaning of random walk actually? We say that we follow a strategy R, okay, or random walk strategy R. Is it a truly random walk, or we should follow some kind of another rule, okay? And if you took a data structure course or maybe a graph traversal algorithms, people, okay, talk about two types of graph traversal algorithms. One is the breadth first search. The other one is the depth first search. Breadth first search does this. Starting from you, I first visit my one distance neighborhoods, okay? So S1, S2, S3, and S4. So these are the things that I can go to using just one hop. That's a breadth first search. After I am done with one distance away nodes, now I can go to S5 because this is two distance away. Then I can go to S7 and S6, these are three distance. Then S9 and S8, these are four distance away, okay? So this is called breadth first search. Depth first search doesn't do that. Depth first search say that I start from one of neighbors, and then from that go to another neighbor of that S4. I should be 2 away from that one and 3 away, and so it chooses the depth first. Depth first search, it chooses the depth. Breadth first search chooses the breadth first. Okay. So these are two different strategies to explore a graph or a tree. Okay. So I can determine my strategy based on these two. Okay. If my strategy is breadth first search, maybe I should visit randomly one of these first and the next and the next and then etc. Or I can come up with a way of combining these two. Okay, some breadth first search, some depth first search. Okay, it's called biased walk. Okay, and if you bias towards the breadth first search, it's called local microscopic view, otherwise global microscopic view. Without going into too much detail, okay, if you come up with P and Q values that measures your localness or the globalness, these are the probabilities. Within that probability, I'm going to do this local search or the global search, okay? And you give these as a parameter, to your random walk strategy and change those parameters. I think I'm going to, yeah, okay. I'm going to give you the final results here, yes, okay. If I do breadth first search, this is what I am doing, those are the strategies. If I am doing the depth first search, these are the stuff. But if I do like P is 1, Q is 2, or P is 1, Q is 0.5, it will differ a lot. And I'm going to be between either this one or that one, not this one or that one. This is all going away. This is all staying around. So I can measure that, I can change that behavior by doing something in between using these parameters, P and Q parameters. Okay, so by random I am not saying that it's completely random, so you should probably choose between breadth first search and depth first search, but not this one or this one. These are two extremes, and giving some weight to one of them but not ignoring the other would be the better solution. That's at least what the experiments show us. Okay, good. Any questions so far? So these are the random walks, and random walks measure what is the possibility of seeing the other node if I am doing a random walk approach. Good, yes.
We do this random walk, for example, testing 10,000 times for the nodes,
Yeah.
and then we calculate the probabilistic. Am I right?
Yes, that's true. Yeah. Well, I mean, you measure the probabilities first, right? You measure the probabilities first between the nodes, and then you come up with your vectors. Okay.
But in your equations, we only saw multiplication of vectors in the loss function. I didn't see probabilistic. In the softmax, we had some summation in the denominator. There were no probabilistic.
Let's go to the loss function. You are talking about the loss function?
Yeah.
Yeah, this one. So you measure the probability between V and this one, okay? The probability between those two. But this probability is calculated by the vectors. Okay? So your vectors are your parameters of the optimization.
My vectors are not probabilities, or
Your vector depends on this probability. Okay? You calculate the probabilities first.
Then I come up with a matrix, and
What do you mean matrix? There is no matrix.
I couldn't understand. And what is ZU? What is ZV?
These are the vectors. Okay, well, if you want to collect all that stuff into a matrix, yes, you could. But this is different from the adjacency matrix. Okay, each node has a. It's like, you remember word to vec? These are your words. We said that we should assign similar vectors to these words because they are occurring within the same neighborhood, right? So we first measured the probabilities that they are occurring together. Then we said that we should assign similar vectors that have higher probability of occurring together. This is kind of the same thing.
We assigning the vectors ourselves.
No, we are assigning it through this optimization.
Optimization, yeah.
This negative sampling optimization. See, this optimization, it talks about the vectors of U and V, U and neighborhood. So this optimization, gradient descent optimization, is changing the values of these vectors. So when I take the gradient of it, I take the gradient of the loss with respect to ZU, ZV, ZU, Z, and R.
Yeah, I understood wrong. That was my problem. I thought that we use probabilistic to calculate those vectors and it is done. But you see, we initiate them, then we use this probabilistic to and gradient descent to optimize those vectors.
Yeah.
This is
okay. So at the end, the probability of seeing another node doing the random walk is fixed for that network, right? So the problem is coming up with this, the vectors to make this operational, this probability assignment. Okay, so that was the hard part. So they came up with this negative sampling because every time I need to calculate this probability is too much, too big. So that's not good. So they came up with this negative sampling, which is, it's not their invention. Somebody else invented it, and they have just used it. Okay, good. So that's a good question. So I am still talking about this stuff. I think let's get the summary and let's move on to next part of the talk maybe. So we embed nodes so that the distances in the embedding space reflect the node similarities. Okay. So we looked at this adjacency based stuff. If they are similarly connected, multi-hop and random walk. Still we did not talk about, or maybe this one, okay? Okay, still we did not talk about your point. How about node features? We didn't talk about that. Also, how about the new nodes? If I have a new node, am I going to calculate all of these together? Okay, like the problem of the word2vec. Word2vec cannot assign vectors to unknown words. Okay, that's going to be a problem. Okay, another question is which one is the better one? I cannot tell you that one of them is better than the other one in terms of their performances, but random walk is more efficient. It is more efficient. So maybe back to your question, how should I choose your parameters? I don't know. I don't have that question, the answer. Okay. So I am going to skip this last part because I am running late. I am going to start with real convolutional networks actually. And with the real convolutional networks, we are going to find some solutions to, okay, some of those problems, graph neural networks. Okay, so this is where we started. Find an encoding, okay, so that this encoding makes the similarity between these two nodes better for the similar nodes. So far, we defined the similarity based on their neighborhoods. Okay, so that's what we did, and I'm going to skip this one. Okay, for the shallow to deep, we only did the shallow similarity. Let's look at some deep ones. Okay, limitations of shallow encoding. Okay, number of parameters is so high, it's a number of nodes kind of thing. They are inherently transductive. That means that it is impossible to generate embeddings for new nodes, okay? And they don't incorporate the node features, okay? More efficiency needed, okay? For the new nodes, we need some kind of a solution for the new nodes. A new node is coming in, and a person is joining to LinkedIn. I need to suggest him something, right? These are your friends, and etc. I need to incorporate the node features. That's what we are going to do now, okay? With the deep embeddings, okay? And then we are going to do this graph neural network, which is going to be logical, okay? You are going to say that, why didn't we think about this before, okay? Okay, good. Okay, basics of the graph neural networks. Again, the setup is similar. A is a vertex set, V is a vertex set, A is the adjacency matrix. We can assume binary or the weighted, doesn't matter. Okay, and now we have the node features. For each node, other than the neighbors, okay, neighborhood information is kept with an A, but for each node now we have the features. For example, categorical attributes, gender, or the person type, text, image, data, and etc. Okay, lots of stuff: node degrees, clustering coefficients, indicator vectors, and etc. They are all possible node features, and it could be very, very large. It could be very, very large. Maybe megabytes of data for each node, and I need to use that one. Okay. The key idea is this: I can represent this graph as a tree. For example, take this node A. Node A has 1, 2, 3 neighbors. Okay, they are kind of connected to that. So A, B, C are here. But for B, C, D are here. But for B, there are 2 more neighbors. For D, there is only 1 neighbor. For C, there is 1, 2, 3, 4 neighbors. So I can do the same representation for that one. So you know where it is going, right? It's like a multi-layered network or something like that. Okay, the features of these comes to a network, and it produces this one and this one and this one comes to there and it produces another result, and I said, so at the end, this is called neighborhood aggregation, okay? At the end, I am going to use, I keep it here, okay. At the end, I am going to use this neighborhood aggregation idea to assign vectors to this node. And the nice thing is that I am considering only the neighborhood of that region without referring to all the other nodes, okay? So if I add a new node to this network, okay, I don't have to recalculate all the other vector assignments. I can calculate this from this structure very easily, okay? This is called neighborhood aggregation, and it's going to be the basics of the convolutional graph networks, okay? Nodes aggregate information from their neighbors using neural networks, and within that, inside that information, I can add features of these nodes into that network as an input. Okay, so I have both the neighborhood information and the feature information. This A and C, I don't consider their neighbors, but I can consider their features, right? So when I am doing this B, C, D, I can get the information from this network, add my features to it, and feed it to another network. Well, this network, and this network are the same actually. They are the same network. So in a way that this is like a recursive network or recurrent network you may call. Okay? Recurring or recursive network. Okay? So every node defines a unique computation graph like that. And using this computation graph, I can calculate the word embedding. The nice thing is that I could use this for word embedding, node embedding, or I could use these networks to make a decision or to categorize these nodes, okay? Is this a green node or black node? Green node or black node, okay? Node type A or node type B. This is a network, and this network can make that decision. Okay, so that's the nice thing about graph convolutional networks. Okay, so this is another view of that thing. So this XA and XC are the features of this A and C. Okay, put them together, maybe average them together inside that network. That network works on it. It produces another feature vector, and put it together with the features of B, and the same thing, and keep running it until you reach A. Okay? Okay? So what is inside this box? Of course, it's a neural network. Neural network of any type that you like. A few layers of network may be there, fully connected, different type. And you're going to see that this idea is very similar to RNNs. If there is an RNN, that means that probably if you keep this number of layers of this network large, you will run into what is the biggest problem of RNNs? What is the biggest problems of RNNs?
Vanishing gradient?
Vanishing gradient. Yeah, you'll run into vanishing gradient problem. So maybe a variation of GRU or LSTM can be used in this case too. So we are going to look at them too. Okay. So how am I going to combine these three things? Okay. Sometimes four things, sometimes three things, sometimes one thing. Okay. They started, okay, always when you start this kind of stuff, a new thing, what are you going to test? Always start with the most stupid idea. Usually it works. So take the average of these three networks, these three inputs. Take the average of it. That's it. Take the average of it. For me, I would have run an RNN here, because I don't know the number of inputs, right? Run an RNN there, and whatever the RNN, so many to one, produces would be your result, and that's what's going to be one of the actually suggestions. But average kind of works. I mean, it's counterintuitive. Why would I add the vectors of three stuff and take the average? But it is good enough, so they just take the average of it for the simple case and apply the neural network of your choice. Very few case.
But not attributes of nodes.
What's that?
We don't average the attributes of nodes. I think we average the vectors of nodes.
Vectors of the output of this network. Okay, here you take the average of these two and feed it to this network. I mean, it is as stupid as, I mean, yeah, I know what you think, but that's how they implement it. These are state-of-the-art stuff, okay? So the idea is new. Let's use a neural network to calculate the embedding of a node. So I have to make a decision now. Let's keep it simple. Let's apply the average and let's see what happens, and it works.
So, but if attributes are quantitative, not, for example, name, you cannot average them.
Well, that's what it is. Well, I mean, if you are using a name, well, usually you use a represent. You don't use the name as the ASCII characters, right? You represent it with a vector. If that vector is a fast text vector, it is based on the characters of it. So Ahmed and Ahmed are very close to each other, or Mehmed and Muhammad are very close to each other. Okay, so if you average Mehmed and Muhammad, their vectors, it will be something similar to Ahmed again.
So we first need to get vector embeddings of our attributes.
Nodes, yeah. Well, that's what I would do, right? I mean, if it's a like age of the person is okay. I mean, I could use it the age, but if the categorical information is, I mean, representing knowledge or what kind of things you should input to your network is something else, right? You know it by now, okay? And dealing with categorical data, like the female or male, red or green or that kind of stuff is difficult. And representing words are difficult too. Okay. Good. So the math is this. You remember this. This looks like an RNN. So at the beginning for this one, okay, I have its feature vector assigned to this internal state, HV0. And then recurrently I run this recursive formula. See, it starts for all the k greater than 0 but not 0. So HV k0 times bk is a matrix, okay, like the bias, and these are weights. And for all of my neighborhood stuff, okay, I average them out. Okay, I take their internal states and average them out with the number of nodes from my neighborhood and multiply it with this matrix. And of course I need a nonlinearity, otherwise that wouldn't be a multi-layered perceptron, and I get my new state. It looks very much like an RNN. Okay, it looks very much like an RNN, but the thing is that these are shared. This W matrix and the B matrix is shared here and here and there and there, like the RNN. Okay, so it is shared. That means that I have a much better chances of opportunities of training these two matrices and getting the results and putting them back in, and I get the final result. So how do I train this? Again, like I train in the RNNs, I do the unrolling. Okay, I do the unrolling of the stuff, and if I unroll it for 5 levels, And well, in this case, I cannot unroll it more than 2 levels, right? Okay, I would have good enough training system, and I will get my results back. So that's as simple as this. Very nice idea. That takes advantage of the whole thing. By the way, our grid-like structures like the images, right? Our images are special configurations of graphs, right? Everybody is connected to, and this one is connected to 4 pixels around it, up, down, left, right, everybody. So I could apply the same ideas there, but convolutional networks are better than that, because convolutional networks are standardized ways of dealing with these kind of neighborhood information. Okay, they are very efficient. Applying this kind of stuff will not help there, because all the neighborhood information is the same for all the pixels. Okay, and their pixel values are maybe the features, just one RGB value maybe. So I don't think that you are going to gain anything out of this kind of a graph convolutional network approach for the images. Okay, but it's a specialization of the graphs. They can be applied, but if you had the CNNs, why bother? That's what I'm saying. Okay, so training the model again, we are going to unroll it, and we are going to calculate this loss function. Okay, by the way, by the way, so how are we going to, okay, so how do we train the model to generate high quality embeddings? Okay, for this A, Z, A. Of course, whoever is close to each other, their vectors should be similar to each other. Okay, that's what I am going to do. I mean, remember the loss function that we have written before. It was saying that the vectors for these nodes should be similar, so their node representation should, when multiplied, should produce nice values. I am going to do the same thing. The only thing is that I am going to calculate the vectors this way. Okay, so what are my parameters? My parameters now are the parameters of these networks plus the assigned vectors. Okay, so my parameter spaces is good. No, it's a little bit, no, sorry, it's not that. Okay, there is no, I made a mistake. No, I'm sorry. The number of parameters for the whole system are just this one and this one. That's it. You don't keep separate vectors for each node. Why? To be able to calculate those values, you just run this network forward. Okay, feed this information forward, and you will get your vectors for that node. Okay. For the optimization, you would produce your vector embeddings in a way that your neighbor nodes have similar vectors. Okay, so vectors are always created on the fly. That's a very different approach than what we had before. Well, in fact, the Glow and FastX and maybe the BERT, they are doing it this way, but it is very different from the word to vec or the node to vec. Okay, so that's the basic idea. Okay, training the model into any loss function like we did before, and run stochastic gradient descent and get these numbers, and that's it. I like to go back to the beginning and line 21 and let's look at this one. Yeah. So the parameters are so large because previously our parameters were our vectors. Now our vectors are not parameters. Our parameters are that A matrix and the W matrix and the B matrix. Now we are not transductive. Why? Because if I add a new node to my network, I can calculate it as a vector very easily without affecting the other. Okay, and previously we said that we do not incorporate node features. Now we are incorporating node features because they are inputs to the neural networks that we are using. Okay, so we did all of them. Okay, this is good, and this is good. Okay, so we are solving many things at the same time. So train the model, unsupervised manner using on the graph structure. Unsupervised loss function could be anything like the random walks, like that we did before. Okay, or as I said before, why bother producing the node vectors if we are going to make a decision about this node? Is this a Twitter account a bot or a human? Okay, I mean, I can get that Twitter user, I can put it in a graph like that, and I can run this experiment if I know some training data. I can do that, and I can do this in a very, very efficient way. I don't have to see the whole network actually. Part of the network I can do this. Okay, so that's the supervised employment of this idea graph convolution networks. Okay, that would be the loss function for you. Okay, that would be the loss function for you. Now, I am not talking about the probabilities of these two happening together. I am talking about getting the correct label. Okay, we have seen this kind of loss functions many times before. Good. So to be able to use this idea, we need to define this neighborhood aggregation function. So far, we have used the average. I don't like it. The mean. Maybe there are some other ways of doing it. And we define the loss function. This one. Loss function, I get it from our previous categorical classification loss functions, or from the previous one, random walk example. We are going to look at this aggregation functions. Okay, I'm going to skip these. By the way, this is inductive capacity again. This is not for a new node. If I get a new node, all I do is I just compute the graph for the B and the A, and I get these values. Okay, inductive capacity. Train on this graph and generalize on a new graph. That's very nice. Train on it and apply it to this one, and it's going to give you some nice vectors back. It's inductive. Okay, so for the aggregation, for the network, for the aggregation, okay, this graph sage is a very famous graph convolutional network. I'm going to show you one example of it. By the way, I think I am running to, okay, so I am going to do maybe 40 minutes of lecture. I am going to let you go. Is that okay? Okay for me. So graph convolutional networks, this guy says that, okay, graph convolution network, this is one of the earliest versions of this graph convolution networks. So I'll say that my internal state will be calculated using this equation. See this one? This one doesn't use any D matrix, just W matrix. And in the neighborhood, it includes itself too. In previously, can I show you? Yeah, okay. Previously, it used to be like this. I multiplied my previous internal state with this pk, okay, and added the results of the multiplication of my neighbor's internal states. This one says that graph convolutional network neighborhood aggregation. No, I am going to include all of my neighbors, including myself, and I will take the average of it. And they say that this works better. Oh, I'm sure they have their own explanation in their paper. I didn't read the whole paper about the explanation. For some cases it works better, and we are going to take their word for it. It's like, I mean, GRU and LSTM. GRU is a simplified version of LSTM, and it works better for some data sets. This is something similar. What's the difference between GRU and LSTM? You are missing one gate. That's it. Okay? You take one gate out, it works better for some data. That's something similar. Okay? And if you do it that way, you can come up with such a nice closed form formula like that. Okay? Represent everything with the matrices, and to calculate this our new state, all you do is just matrix multiplication. Okay, so mathematically is efficient and elegant, and time complex is the number of edges overall. It's not the number of nodes, number of edges. Okay, so that's the graph convolutional networks. Let's look at this graph Sage. Okay, so what is the aggregation way of doing it? This is now our aggregation function. Previously, we used to take average of it, but we can put anything that we like around here. And let me show you what the alternatives are with the graph Sage. Okay, this is the classical one, the mean, the one that we don't like. The other one could be pooling. Remember the max pooling approach of the original multi-layer networks, or the convolutional neural networks? The same idea is here too. I mean, don't take the average, just take the max pooling. Okay, choose the maximum one from each of those. Or the idea that I told you before, why don't you run an LSTM between these? Okay, since I don't know the number of inputs to this node, instead of taking the average, or instead of taking the pool of it, so why don't you run a recurrent neural network here? It's going to be like many to one network. Whatever this network outputs, it will be output of your network. So you will end up introducing more parameters to your system. Okay, but it's going to be worth it for some cases. By the way, did you see this? For LSTM or RNN to work, you need an order, right? But these don't have orders, right? This one, A, B, C. What is the order? I don't have the order. There is no order of neighborhoods, okay? What are the orders of the neighbors of the C? B, A, E, F, or E, F, A, B? I don't know. So this one says that run an LSTM, okay, with the random permutations of the neighbors. That's what it says. So run it many times, and after that, use its output.
Expensive.
Yeah. Well, people are smart. Okay. I mean, some of them are smarter than myself. Yeah. Okay. Well, I mean, this deep neural networks, after this much success, okay, people from all the areas of science and engineering, they made lots of contributions. Okay. If thousands of smart people are working on something, some of those smart people are going to say some very smart stuff, and other smart people will accept it. So more people works on it, it's going to be something that you don't expect. Okay, very fast development is going to happen here. Okay, so gated graph neural networks is the same thing. When you are training this stuff, you do the unrolling, and that means that, okay, that means that if you do it too much, your gradient flow will be slower and slower, and that will be the vanishing gradient problem. So why don't we use, okay, so this is 2-3 layers deep. If you make it deeper, if you make it deeper like 10 layers, then the gradient flow problem, and in that case, use techniques from modern recurrent neural network, which is gated recurrent units or the LSTM. Okay, so that's what the gated graph neural networks are. Okay, apply in this direction. Previously, I applied LSTM here or RNN here. Now I am going to apply LSTM in this direction. Okay, okay, RNN module. So that's what I'm going to do now with the GRU. So I'm not going to look at the details again. I don't have much time for this. I like to spend some time for the applications. Good. So that's the gated graph neural networks. Okay, so let's look at this last part of subgraph embeddings. So maybe I should ask you this. I mean, if I wanted to assign a vector to this subgraph of this graph, what would you do? That would be nice, right? I mean, let's say out of all the Twitter users, I like to assign a vector to the Twitter users of this university, Gebze Technical University. I have total of 5,000 people maybe out of this university. Okay, I like to assign a vector to this university's people, just a single vector, so that I can compare that vector with the people of the Istanbul Technical University maybe. Okay, how similar are they? That would be nice, right? So how would you do that?
Looking to the X matrix, looking to the attribute matrix, and categorizing the nodes.
Take the attribute matrix and then what?
If all of the nodes share the same attribute in those.
They don't share. Well, I don't know what's happening. I mean, all I want to say is that I like to assign a single vector to all the people of Gebze Technical University on Twitter.
Then we should know first which one of these nodes are in Gebze Technical University.
Well, yeah, but of course I know that, yeah.
So now we're gonna.
So what would you do? One of the ideas is very simple.
Maybe
Just
average them all.
what?
Average them all.
Average them out, yeah. One thing, well, take then what you do? You mean take all the vectors and average them out. That's one thing. Or thing could be, let's combine them into a single node. Call it GT. Okay. So my network would be B A B GT, right? And like that, A, B, and this would be my new network, right? So calculate the embedding for GT now. Or if you are doing some kind of a categorization, for example, is GT a bot? Okay, you can write there. Okay, so the possibilities are endless once you have this kind of a structure, right? Previously, if I do that with random walks or the adjacency matrices, I have to calculate all the vectors all over again. Now I can do that. So let's look at the other approaches for the subnetworks. Okay. Okay, this is the original network. I like to assign this one. Simple idea is your idea, just average them out. And it is done. You cannot publish that idea anymore. Sorry. The second idea is, okay, virtual node. And it is done too. Okay, and it's still an open research area. If you have other ideas, then for example, I mean, the relationship between them, inside them is important. Both of them are kind of ignored, both averaging them out and using this as a virtual node. Both of them ignore that kind of an idea. Maybe we should use that idea too. I don't know. Okay.
Max pooling, it can be idea.
What's that?
Max pooling, can we use that?
I mean, what is the meaning of choosing the maximum of each vector element? Well, it would be similar to, yeah. I don't know, maybe, yeah, maybe, yeah. Maybe you should come up with a new vector, new network that calculates this one based on the similarities of the universities, or I don't know. I mean, again, it's a research area. If you are interested, just okay. Always look at these kind of problems, what you can do with your own research. Okay, I am sure whatever you are looking at in your project, you can come up with a network. Okay, networks are very. I mean, the sentences are networks, right? This is a node connected to this one, connected to this one, this one. This is a very simple network, right? So it's a sequential thing, but it's a network. Okay, so
maybe all sentence is connected to each other.
maybe you could. I mean, later maybe you can think about that too. Yes, that's true. And how to do analog of CNN? So, for example, the analog of CNN is a word phrase. This one, so it's a subnetwork. So if you think about it, you can come up with these kind of ideas, and in your original research area, you can apply these techniques, and maybe you can come up with new ideas that are applicable for the general networks too. Okay, now finally, I like to talk about some applications. I did it. Okay, wrong river. Let me open the. This one again. So applications, I am going to look at recommender systems, like the one that we talked about all the time, and the computational biology, very important application here. Very nice paper. Let's look at this. Random walk graph convolution networks, okay, graph sage, to make recommendations to millions of users on does anybody use this Pinterest? Okay, Pinterest is this. Maybe you know it. Okay. So we have a graph. Bipartite graph is this. Bipartite graph is this. You have two subgraphs inside the bipartite graph. Okay. These are the items. These are the users. It's like an Amazon graph. You have your products. You have your persons by products. So this user has connections to these items. This user has connections to these items. This user has connections to that items, etc. So this is a bipartite graph, okay, for recommendation systems. Recommendation systems are like for the Netflix, you have the users and you have the movies. For the Amazon, you have the users and you have the items. For universities, we have the universities and we have the students, right? Each student is affiliated with one or more, or maybe I should say we have courses and we have students. Okay, what else? For classes again, for courses you have the students and the courses. So these kind of graphs are very common. So it is two subgraphs. One side is users, the other side is items, movies and the users, etc. and etc. So in recommender system, it's the same thing. It's the same thing. So if I have a new movie, I added this movie inside this graph. Okay, a few people watched it. I have now the embeddings for this movie now. Can I offer this movie? What kind of people should I offer this movie to? Okay, so that's a recommendation system. I get a new product from China now, even via Amazon. Which person should I offer this product? Okay, when they open my Amazon web page. I am offering a new course next semester. Okay, we are offering a new course next semester. Actually, it is called neurocontrol, Erkan Hoca, myself, Yakup Hoca, and Erdoğan Hoca is the neural nets for the control control theory. Okay, it's called neurocomputing. So what students should I offer this course to? I mean, which ones should I send an email to? It's again recommendation system. Okay. So what are we gonna do? That's we are trying to solve with this random walk graph convolutional neural networks. And by the way, okay, this is 2018, right? So this is under review, but it is published. So this is a few years old stuff. So let's look at the system details. Two sources of information: the content features, what kind of product, movie, course I have, and the network structure, user item interactions. Graph neural networks works naturally to incorporate both of them. So Pinterest, okay, pin, yeah, the users, okay, they pin whatever they like on the network. Visual bookmarks, someone has saved from the internet to a board they have created, and those are the pin features, okay. So users pin some of the content to some boards, okay. So it is interest and pin put together, it's called Pinterest, okay. So this bookmark is pinned to one of these boards. I don't know why do you pin a context a context to a board. I mean, why do you do this? You become popular. Why would you use such a system? To communicate with your friends? Because I am not a social media guy, so I don't know why people would use Facebook or WhatsApp or Twitter.
Can you ask the question again?
What is the motivation for Pinterest? Why would you use such a thing?
It's a very useful thing, Hocam, for finding ideas.
And it recommends very unique photos. I am using Pinterest and I am following some artists and they recommend so many.
So you follow your boards, these boards?
Yeah.
So you look at one of the boards and
folders to images and they recommend.
so okay, so you do this for searching stuff?
Yes.
Of your interest? So you do pinning too?
Yes, I am pinning.
Okay, so
And
you are one of the users.
Like folder.
Okay, so you are one of the users of Pinterest, and I don't understand what you do, why you do it. So that's good. So
Hocam, it is the recommendation. The recommendation system is very good. For example, you are searching for furniture. You are searching it for 2 hours. After 3 hours, you come back and you see some beautiful stuff recommended for you.
really?
Maybe get some good ideas.
Oh, okay, good. So it's a very large data set. It's a naturally graph, right? It's naturally a graph. There are nodes and there are nodes and they are connected, and it's a bipartite graph. Okay, there are boards and there are, what do you call this? These are features. Okay, these are pins. Okay, so I pin this content to this board and etc. So the recommendation is, I mean, should I, if I have a new content or some unrelated content, should I pin this content to one of those, right? So that's the thing. Okay, if it is my source pin, okay, should I recommend this board or that board? The thing is, there are 3 billion pins and boards, and there are 16 billion interactions between them. It's very, very large, and whatever you are pinning is not a single text. You are pinning the whole content. It includes image, text, features, sometimes videos. Does it include videos too? Videos?
Yes.
Yeah.
Okay, so maybe I should try it. Okay, so random walk graph convolution networks. Okay, just architecture is just an extension of graph sage, whatever we were doing. Okay, So you follow this, and here aggregation function is element-wise mean or max. Okay, so it is not using LSTM, mean or max, like the pooling, and you assign these kind of vectors to the nodes, new nodes. Okay, and these are the steps: collect billions of training pairs from user logs, train the system to generate similar embeddings for training pairs, and I can generate embeddings for all pins, and then later I can make recommendation saying that this content is suitable for this board. Okay. Okay, so and they are using again this negative sampling. This is the loss function. UV is the training pairs from user logs. This user log, this one, and so the vectors between these two should be similar. Whatever I did not pin should be like this is minus, this is plus, and there is a margin. Okay, this is called max margin loss. Okay, I want it to be maximum, but I want it to be larger than this delta, sorry. Okay, so again I'm going to skip the details of it. Very difficult problem because it is 10,000 times larger than any previous graph neural network application. So you have to use specialized architecture for GPU, CPU usage. Also big data, right? I had to use map-reduce structures. Okay, so I will skip the rest of it. This is one example of using stuff. This maybe Jacopo talked about this. Where is it? Yeah, curriculum learning. In the curriculum learning, you start with the easy stuff, like the curriculum. When you teach something to people, you start with the easy stuff, and then you teach them hard stuff later, right? Or give them as an exercise. It's kind of like that. It uses those. Okay, so performance is very impressive. 72% better recommendation than standard systems. Okay, and in fact these are the numbers compared to the other ones. Okay, good. This one is even better. It appeared in here, and I thought this one was a Nature article, but it is not, I guess. Okay, graph convolution approach to polypharmacy side effects. This is the problem. I have a pill, I have a drug, it's good for this kind of a disease, and it doesn't have any side effect. I have another pill, it is good for some other kind of disease, and it doesn't have a side effect. But if I take them together, it produces some side effects like headaches and the coughing and etc. Very nice graph, right? So we like to find these. I mean, they said this is a very difficult problem because the number of ingredients of these drugs is very, very, very large. Making experiments on people with the combinations of these drugs is expensive, and most of the time you are not allowed to do that kind of experiments on people. Okay, if you are going to do the experiments randomly, then you should choose your candidates in a very smart way, and this is all about that. So what are we going to do now? We have drugs, we have the side effects. Again, bipartite graph. If I can ask questions, are there any side effect relationships between this drug pair and this side effect? Okay, can you tell me the probability? If there is a high probability, then you run your experiments on it, and you say that this combination causes this side effect, and you are doing this on computer without doing any, okay, any experiments on people. Very big market. In USA, it is We are talking about $177 billion of cost annually, because people are having these kind of side effects if they use two drugs in combination. Okay, systematic experiment is challenging, it is expensive, you are not allowed, it is not ethical, and etc. So computational stuff. So this is what we are going to do. We have the drugs, we have the genes. Okay, bipartite graph again, and these are the real stuff inside the drugs that are effectively causing these kind of healing or the side effects and etc. And they are related with the genes. If I can have such a network, okay, there is a known network actually. I mean, I know that this substance is interacting with this kind of a gene. Okay, I know that, I know all the results of it, but most of the pairings I don't, especially with the combinations of it. Okay, combinations of it. For example, I know that between this ingredient and this ingredient, there is an edge, and it is called R2. R2 is a bradycardia effect. Okay, something related to heart, I guess. And R1 is gastrointestinal bleed effect. Okay, very bad effect.
If they are used together.
What's that?
If they are used together.
If they are used together, yeah.
Side effect.
Yeah, if they are used together. Okay, so I know some part of this graph, and I am going to ask the same question between this one and that one, maybe between three of them. Okay, so the labeled edges between drugs predict the likelihood that an edge exists, meaning is drug combination is the polypharmacy side effect. So they did this, and I am going to show you just the results here, and that will tell me the, okay, data is molecular protein-protein interactions and drug target relationships, and there is the patient data of the side effect, and okay, these are the area under the curve, okay, area under PRC and etc. Okay, up to 50% improvement over the baselines. Okay, it is, of course, I mean, you don't believe these results because it's the first opportunity to computationally say that there is a potential of interaction here, bad interaction. So you should be careful. Maybe you should run some experiments on people in that case. Okay, so that's the prediction performance using the ideas of graph convolutional networks. Okay, so I guess that's going to be it. Rest of them, by the way, these kind of stuff are not difficult to apply in TensorFlow. I mean, I didn't show you any new ideas about the neural networks, deep neural networks, or the other stuff. All I did was using whatever we know before, and we applied to new areas of the graphs, and the results are very, very promising. And again, it's not a niche area. You have seen examples of graphs everywhere, networks everywhere, so it is applicable to many other places. That's my conclusion. And many libraries, deep learning libraries, are supporting this kind of stuff. Okay, so TensorFlow, this one and this one, Torsion, yeah, they are all available. Good. Any questions?
John, can you go to the last slide?
Can I go to the last slide? Even this one?
The most of the things we talked till now was the node embedding. Am I right?
Node embedding is
part is the node embedding.
Yeah. Well, there are many ways of doing the node embedding, including the shallow node embedding. That starts with the neighbors only. For most of the problems, that's going to be enough actually. Node embeddings, the interaction between them. But if you start including more data about your nodes, your features, then graph convolution networks, And if you're concerned about what am I going to do with the new data, new nodes, then definitely graph neural networks.
Sir,
Yes.
I have a question. How do you handle edge features, edge labels?
Edge labels can be represented using the adjacency matrices. Remember? Remember the
label value into adjacency matrix.
yeah. It is in the adjacency matrix when you multiply two vectors together and subtract the adjacency value from it. So that shallow networks can handle that information.
What about edge attributes?
What about?
If we have edge attributes, not only one label but
More than one?
Yes, more than one.
Well, in that case, that's going to be a feature, right? How would you do that? I didn't see. I don't remember people using it. If you have more than one edge between two nodes, two relationships between them. Maybe for each edge assign a different. It's like yeah, word to vec. You know, some of the words have different meanings, right?
Yes.
So if you think about jaguar, jaguar is an animal. Jaguar is a brand name. Jaguar is a Java library or something like that. So, and it looks like there is only a single word jaguar, but there are three different words. So if you have two different edges between, what does it mean that you have a two different edge between, for example, two people? They are both friends, and maybe one of them is the brother of the they are siblings, right? So that's the relationship between them. Maybe just introduce another dummy node into the graph to represent that person two times. Okay? One is the brother person, one is the worker person, and they have their own. It's just a solution just I made up. Okay? I don't remember it. Or you what?
Introducing dummy node for every node means two parallel networks.
Well, it is not parallel. They are yeah. They know each other. Maybe they are connected to each other as like self, right? I mean that person and the brother person and the co-worker person, okay? And each one is connected to the other one as a self property, but each one is a different person in my network and your network. I don't know, it might work that way. So, I mean, we have the same problem with the word-to-vector representations too. Maybe I shouldn't assign a single vector for some of the words because they function differently when the context changes.
So I think I can think edges as nodes.
Yeah.
And each edge has two nodes. Take edge features and those two nodes features, attributes together, and take derivative of graph and use edges as nodes. Maybe
it could work. It could work when I add a new node. When I add a new node, I have to add lots of nodes to your graph.
Yes.
Well, that might be a little bit.
When I add a new node and it has three edges,
yeah,
I need to add three nodes to derivative of graph.
And so your nodes are okay. You are just changing nodes with the edges.
Yes.
Yeah, it might work. Yes. Well, I mean, as the slide says, this is a new area, and you can do whatever you want as long as it works.
Final question. In node embedding, we didn't use any neural network. Am I right? In the first
for node embeddings, we did not use any deep networks. No, it was very similar to word to vec, very simple one hidden layer network to assign the to assign the parameter values to those vectors.
Thank you.
Okay, good. Okay, thank you. I'll see you next week.
Hocam nöral kontrol dersinin içeriği